So the question we're covering now is question 7, 2015. This is an Enols and Enolates question. Part A, you have an aldehyde reacting with base, treated with water to give a final product. All you're told is that it is C6H12O2. So it should be given in already, but because there's 6 carbons, you're going to have the aldehyde reacting with itself. So attack with the base will attack one of the acidic alpha hydrogens. This will pull electron density up into the oxygen, giving you this structure here. The electrons will then return to form double bonds. The alkene double bond will attack the electrophilic center. The electron density will move up into the second oxygen to give you this structure here. This negative charge is then treated with water, steals one of the hydrogens, and end up with this product here, which is a beta hydroxyl aldehyde. So part B of this question involves these 2 compounds here reacting with an unknown base. Second step is an acid workup to give you this 1,3-dicarbonyl product here. And you're told that this is a cross-Claisen condensation reaction. So, first thing you need to know is what base you need, and also which solvent, which is important in the question. As you can see here, the base of choice would be sodium ethoxide, and the solvent is ethanol. This is to prevent any unwanted side products, because the charged species in the reaction match those that are present in the molecules you're working with. You have one enolizable carbonyl, like here, and one non-enolizable carbonyl. This ensures that you can control the product outcome. Attack of the base, one of the alpha acidic hydrogens. Electron density moves up into the oxygen, giving you this here. This will then react with your non-enolizable carbonyl. Electron density will move up into the oxygen again, giving you this species here. Your double bond is going to reform. You will lose one of the ethoxides to give you this here. And this is just a quick summary. The base is just going to keep on attacking these hydrogens here. The only way to prevent this is with a hydrogen workup, which will leave you with your final product here. So the final part of this question, part 1 of C, asks you to draw the resonance structures of F. This is the molecule F. So it only has one resonance structure, as shown here. The electron density moves up into the oxygen from the alkene, getting this form here. And because this is a resonance structure, it comes forward and backwards. It also asks you to determine the electrophilic centres. So electrophilic centres are any centres that would like more electron density. This is denoted with this little asterisk here. The reason that this is an electrophilic centre is because electron density is being pulled away from that carbon by the oxygen. You have the same thing here. All the electron density has been pulled away into this alkene and also into this oxygen up here. Part 2 asks for the product of the reaction of these 2 structures here, followed by an acid workup. So you know, just by looking at this structure here, that you have an enol. You also have the same molecule here, molecule F. The electron density is going to come down from this oxygen. Double bond electron density here is going to attack this electrophilic center, like we were just talking about. And this is going to grab one of the hydrogens from the acid workup. This isn't a complete mechanism, but it doesn't ask you for a complete mechanism, it just asks you for the product. You'll end up with this messy product here, because there are no good leaving groups on the molecule, so you won't have a dicarbonyl, you'll have a beta hydroxy molecule. Part 3 asks what happens when you treat molecule F with lithium aluminium hydride, followed by an acid workup. Lithium aluminium hydride is an incredibly powerful reducing agent. It will react with the centre here, giving you an alcohol, but it will not attack here because this is a hard nucleophile. This is a hard centre, whereas this is a soft centre here.